How many joules are needed to warm 25.5 grams of water from 14 degrees Celsius to 22.5 degrees Celsius? Well, we're definitely going to be using Q equals mc delta T for this problem because we have mass and we have temperature change. And we're also asking for joules, which means we need to find Q. Now, this problem doesn't explicitly tell us what the specific heat of water is, but this is something I would give you and you would be able to look up. So all we have to do is plug in the information. We have 25.5 grams. We have the specific heat of water, which is 4.184 joules per gram degrees Celsius. And we have the temperature change. Remember, it's final minus initial. So the final temperature is warmer. It's 22.5. We subtract the 14 degrees from that. Once we have it all set up, we can see what cancels. Our grams cancel, our degrees Celsius cancel, and our answer is in joules. And that answer with correct sig figs is 907 joules. Calculate the number of joules released when 75 grams of water are cooled from 100 degrees Celsius to 27.5 degrees Celsius. Again, we're going to need Q equals mc delta T. We have 75 grams of water. We have the specific heat of water. And again, final minus initial. That means since it's cooling down, it's 27.5 minus 100 degrees Celsius. We're going to end up with a negative number, and that matters. Our grams cancel, our degrees Celsius cancel, and our answer is in joules. Notice this time our joules are negative. It's negative 22,800 joules, and the negative means that heat is being released, and that is exactly what we see in this problem. Calculate the heat in joules needed to warm 225 grams of water from 88 degrees Celsius to its boiling point, 100 degrees Celsius. Again, this is a Q equals mc delta T. We plug in our 225 grams, the specific heat of water, 4.184 joules per gram degrees Celsius, and the temperature change, 100 minus 88. Grams cancel, Celsius cancels. Our answer is 11,300 joules once we use correct sig figs. Number 4. The specific heat of gold is 0.128 joules per gram degrees Celsius. How much heat would be needed to warm 250 grams of gold from 25 degrees Celsius to 100 degrees Celsius? We're going to use Q equals mc delta T, and we have all the information that we need. We have 250 grams of gold, we have the specific heat of gold, and we have the temperature change, 100 minus 25. Our units cancel, our answer is in joules, and using correct sig figs, it's 2,400 joules. The specific heat of zinc is 0.386 joules per gram degrees Celsius. How many joules would be released when 454 grams of zinc at 96 degrees Celsius were cooled to 28 degrees Celsius? Again, we equals Q equals mc delta T. Our grams are 454 grams, the specific heat of zinc, and then the final minus initial temperatures, which in this case will be negative, so it is cooling down. Grams cancel, Celsius cancels. Our answer is negative 11,900 joules. Remember to use sig figs. Phileas Fogg, the character who went around the world in 80 days, was very fussy about his bathwater temperature. It had to be exactly 38.0 degrees Celsius. You are his butler, and one morning while checking his bath temperature, you notice that it's 42 degrees Celsius. You plan to cool the 100 kilograms of water to the desired temperature by adding an aluminum ducky, originally at freezer temperature, negative 24.0 degrees. Of what mass should the aluminum ducky be? You have some information here. The specific heat of aluminum is 0.9 joules per gram degree Celsius, and the density of water is 1 gram per milliliter. Now that number might not really be significant to us, but it's a fact that we can keep at the back of our brains. So we're going to also assume that no heat is lost to the air. So in a big problem like this, the first thing you need to do is pull out key information. We have a final temperature, which we want to be 38 degrees Celsius. We have our initial temperature, which is 42 degrees Celsius. We have 100 kilograms of water. We have a very cold ducky at negative 24.0 degrees Celsius. And we know that we need to find the mass, and we have the specific heat of the aluminum ducky. Now, the density of water, again, not sure if we'll need this or not, but we have it just in case we do. Apparently, there are several different size duckies in this freezer, so what we're trying to figure out is which size ducky we're going to need for Phileas Fogg's bath. Let's start with our water information. We know we're going to use Q equals mc delta T, and we know all the information for water. We know that 100,000 grams are used, and I know the problem said 100 kilograms, but you'll need to do some dimensional analysis to get to grams. The specific heat of water is 4.184 joules per gram degree Celsius, and our temperature change. We're starting at hotter water than necessary, and we want to end at 38 degrees exactly, so final minus initial. The amount of heat will need to be negative 1,670,000 joules. The ducky then will have to be able to absorb 1,670,000 joules. So, with that in mind, we can set up a new Q equals mc delta T equation. starting with the 1,670,000 joules that the ducky will need to be able to absorb. So we need to find the mass of the duck, we know the specific heat of the aluminum duck, and we know the temperature change. It's going to go from negative 24 degrees Celsius to positive 38. So it's final minus initial, which means it's 38 minus a negative 24, and in that case, that means you're going to actually add them together. So we'll divide both sides to get rid of the specific heat and the temperature change, so we have mass by itself, and those will go away because they're equivalent to 1, and our joules cancel, our degrees Celsius cancel, and our answer will be in grams. So what we get is that the final mass of the ducky will be 29,900 grams, or 29.9 kilograms. I'm not sure how big that is in terms of aluminum ducks, but he's going to have a big duck in his bathtub. Maybe the butler, you, could take it out before Phileas Fogg gets in the bath, because if he doesn't know what's in there, he's going to be in for a surprise. A certain material's temperature increases by 1 degree Celsius for every 1,560 joules that it gains. A 0.1964 gram sample of quinone, molar mass of 108.1 grams per mole, was burnt, and the surrounding material's temperature increased from 20.3 degrees Celsius to 23.5 degrees Celsius. Find the molar heat of combustion for quinone. Well, let's look at the information we have here. We know that some substance will increase 1560 joules every degree that is raised. And our sample, we have 0.1964 grams, we know the molar mass of that sample, and we know the temperature change of the surrounding material. The question asks for molar heat of combustion. Now what that means is how many joules per mole are released during this reaction, during the combustion. So ultimately what we want to know is joules, and then divide by the number of moles that we have in the sample. So there are a couple of steps we need to do here. First, we need to write out the material information. We know that the change in temperature is 23.5 minus 20.3 because it's final minus initial. And that gives us a temperature change of 3.2 degrees Celsius. Well, if we have 3.2 degrees Celsius and we know the rate at which the heat will increase per degree Celsius, then we know we can do some dimensional analysis here, where 1 degree Celsius will cause 1,560 joules to make it go up that degree. So basically, it's going to take 5,000 joules, or 5 kilojoules, of energy for the 3.2 degrees Celsius change. Now, the molar heat of combustion, again, is joules per mole. So we started with 0.1964 grams of quinone. We need to turn this into moles, because it's not joules per gram, it's joules per mole. In order to do that, we're going to use the molar mass. So 108.1 grams on the bottom and 1 mole on top, and that means we're going to have 0.00182 moles of quinone. So now what we have to do is take the joules and divide by the moles to get joules per mole. Now, in reality, you have to remember that this reaction is releasing heat. It is exothermic, so it's actually negative 5,000 joules because heat is being released, divided by 0.00182 moles. And that will give us negative 2,700,000 joules per mole, or to make it a little less beefy looking, you can say negative 2,700 kilojoules per mole. A 1.55 gram of CH4O sample is burnt in a calorimeter. If the molar heat of combustion of CH4O is negative 725 kilojoules per mole, and assuming that the 2 liters of water absorbed all of the heat of combustion, what temperature change did the water experience? Well, we have some information here. We've got the grams, kilojoules. We want to know temperature change. So what we should do here is first go from grams to moles, and that will give us the number of moles of the CH4O, because we were given molar heat of combustion. So we need to be able to get rid of these moles and just get our answer in joules so that we can actually use an equation here. So with a little dimensional analysis, you find 0.0484 moles of CH4O. Now we can take that number and use the negative 725 kilojoules per mole as a conversion factor. We set that up, moles cancel, and you have your answer in kilojoules. So it's negative 35.1 kilojoules. So that means when this is going to combust with the number of moles that we have, that's how much energy is being released. Now our problem's not over. It wants to know what the temperature change of the water is going to be. So we take our value of heat, and we're going to use this as Q in our Q equals mc delta T equation. If we know that the water is going to absorb that amount of heat, then we can set it to positive 35,100 joules, which is the same as 35.1 kilojoules. We know that there are 2,000 grams of water. I know that it said 2 liters of water, but remember, 1 milliliter of water is the same as 1 gram. So if we go from liters to milliliters, then there are 2,000 milliliters, which means there are 2,000 grams. We have the specific heat of water, and we need to find the temperature change of the water. So we just do a little bit of algebra here to rearrange our equation. Our joules cancel, our grams cancel, and we will receive an answer in degrees Celsius, and that is 4.2 degrees Celsius. In real calorimeters, most of the heat released by the bomb, by the way, it's called a calorimeter bomb, which sounds way cooler than it actually is absorbed by water. But a certain amount is also absorbed by the metal and insulation surrounding the water tank. A certain calorimeter absorbs 24 joules per degree Celsius. If 50 grams of 52.7 degrees Celsius water is mixed with the calorimeter's original 50 grams of 22.3 degrees Celsius water, what will be the final temperature of the mixture? Well, this problem has a lot of information in it. Basically, we've got the 24 joules per degree Celsius that the calorimeter absorbs. We have the 50 grams of 52.7 degree water that's being mixed in with another sample of water that's the same size and has 22.3 degrees Celsius water to start. And we want to know the final temperature. Now, this might seem really complicated, but basically what we're going to do is one big, fat algebra problem. So get ready, because algebra is super awesome. Here we go. The basic idea here is that the hot water is going to lose heat, and the other two things, the cold water and the calorimeter, are going to gain that heat. We can't just create or destroy the heat, it has to be transferred. So we know that the amount of hot water heat lost will be equal to the amount of heat the cold water and the calorimeter will both gain. So we can set up this equation. Negative Q of the hot water equals Q of the cold water plus Q of calorimeter. Now, what we're going to do is take Q equals MC delta T and do some sweet algebraic substitution in this equation. Now, don't freak out, it's just full of awesomeness. Basically, what we have here is negative MC delta T, which is what Q is equal to, equals the MC delta T for the cold water plus the 24 joules per degree Celsius times the change in temperature that the calorimeter is going to absorb. Now, we don't need to use necessarily the MC delta T because we were already given that it's going to be 24 joules per degree Celsius for whatever the amount of change is. Now, the other thing we need to know is what the final temperature of this water is going to be. So we can't just say what's the delta T, we need to know what the final temperature is. So we're going to substitute in, instead of saying delta T, we're going to do T final minus T initial. So this is what it looks like. MC, T final minus T initial. Same thing, just put that in for more specificity. Now we can actually start putting in some numbers. The negative 50 is for the first sample of water. The 4.184 is the specific heat of that water. Then we have the final temperature, which we do not know. We're going to subtract the initial temperature, which was 52.7 degrees Celsius. Now for the cold water, it has also 50 grams that it starts with, 4.184 joules per gram degree Celsius of the specific heat. We don't know the final temperature, but we do know that it started at 22.3. Now for the calorimeter, we know that it's going to require 24 joules every degree that it goes up. It's going to suck that heat out. And we know that it also starts at 22.3 degrees because the cold water is there and they're going to have the same temperature. So again, we're trying to find final temperature in that case. So we have TF in several places. What we need to do is rearrange this so that the TF is all in the same spot. So we'll start to do math, algebraically solve this as we go. So the first thing I'm going to do is just multiply out the things that are kind of straightforward. So 50 times 4.184 is 209.2. And then after the equal sign, again, we have 209.2. And then we have the plus 24. Now, 209.2 plus 24, the TF minus 22.3 and TF minus 22.3, that's the same. The 209.2 and the 24, what I need to do is add the 209.2 to 24. And what you get is 233.2. The next thing we can do is divide both sides by the 233.2, and we'll get negative 0.897. And then we have TF minus 52.7 equals TF minus 22.3. Now next we'll distribute the 0.897 to the TF and also the negative 52.7, and what you get is negative 0.897 TF plus 47.27 equals TF minus 22.3. So now we can add 22.3 to both sides, and that will get rid of it from the right side, and we can also add 0.897 TF to both sides, and that will get all of our TF values on one side and the other numbers on the other side. We get 69.57 equals 1.89 TF. Lastly, divide both sides by 1.897, and you get a final temperature of 36.7 degrees Celsius.